Hey everybody, today we're going to look at what's called chemical equilibrium, okay? And to give you an idea what chemical equilibrium means, I'm going to start with a towel, okay? I know this kind of sounds weird, but kind of bear with me here. All right, but I'm going to start with just a towel, not any ordinary towel, a red towel. Okay, not just a red towel, but a wet red towel. Okay, so we got water in this towel. Okay, so what the heck am I talking about here? All right, what I'm referring to is that the fact that we have this towel and it's got these water molecules in here. Now, if I leave this towel in an open room, what'll happen is that these water molecules will eventually go off into the gas phase and the towel will become dry, right? So we all know that this is what's going to happen. Now, if you remember back when we talked about um, thermochemistry, and we talked about systems being open and closed. Well, this would be considered an open system. These water molecules will eventually all go into the air, into the gas phase, and the towel will then become dry. This is why we can, we hang up our laundry and let it air dry sometimes. Or back in the past, we used to put it on clotheslines and let it dry in the open air in the backyard. Eventually, all the water particles would go into the air. This is not equilibrium. What if I were to do the same thing, but instead of doing this in, open into the environment, what if I were to put it in a container? Okay, think about what would happen if you were to put your this wet towel into a gym bag. Let's say you're at the health club or working out and you have a wet towel and you throw it in your gym bag and you close up the gym bag and you keep it closed. Well, will that towel be dry eventually? Well, no, because what's going to happen is as these water particles build up at the top, right, these water particles are going into the gas phase. Eventually, what's going to happen is you're going to get a lot of these water particles in the gas phase, and some of them are going to come back down and condense back into the liquid on the towel. What's going to happen is these are going to keep going back and forth into the gas phase and eventually into the liquid phase. And this is what's referred to as equilibrium. This is it's referred to as a dynamic equilibrium. What will happen eventually is that the rate at which the towel or the water goes into the gas phase will equal the rate at which the water particles go into the condensation or go into the liquid phase. So our rate of condensation, okay, our rate of, let's say, evaporation first, our rate of evaporation will equal our rate of condensation. When those two rates are equal, the towel will stay wet and the particles in the air will stay equal. So what that means is I will not change the number of water molecules in the air and I won't change the number of particles on the towel. It doesn't mean that the number of particles in the air is equal to the number of particles on the towel. That's not true. What's true is that the rate at which they change is. So what I mean by that is if I have one, let's just say for the sake of simplicity here, one of these goes into the water, well, another one is going to go back into the gas phase. One of these goes into the liquid phase. Another one goes back into, whoops, kind of turning it around, goes into the gas phase. And I still have 3 and I'll still have, what, 6 down here. So as this one comes down here, this one goes back. Another one will go back up. I'm kind of getting sloppy here with my pictures, but you hopefully get the idea. So hopefully you know that if you put a towel into an open air, you're going to end up with a dry towel. If you leave it in a bag, it's going to stay cold, stay wet. That is referred to as equal. It's called a dynamic equilibrium. The equilibrium is only achieved when the particles are, when it's in a closed container. So let's take a look at transferring this to chemistry. Let's say I start with nitrogen gas, okay, and I'm going to react that with hydrogen gas. So these are the two reactants that I'm going to put into a container. So let's say I have a container, and I have inside of that container nitrogen gas and hydrogen gas. Okay, if I have these two gases in the same container, what's going to eventually happen is that these are going to react, and they're going to produce ammonia, NH3. Okay, now the balanced equation for this would be to have a 2 here and a 3 here for the balanced equation. Alright, so the balanced equation is important right now, but it will be in a little bit. We're just looking at this qualitatively. So, produces ammonia. So in the beginning, I have hydrogen and I have nitrogen, but I don't have any of the ammonia. So the ammonia is not in the container. But as the reaction proceeds, as it reacts, this is going to go down, this is going to go down, and this is going to go up. Notice this is decreasing, the amount of hydrogen and the amount of nitrogen is decreasing while the amount of ammonia starts to increase. Well, eventually, at some point in time, they no longer change it anymore. They're now going to be the same. So as I build up the ammonia, Okay, the reaction is going to start to build up enough ammonia that the ammonia is going to break back down into nitrogen and hydrogen. Okay, so we have the reaction occur, creates the ammonia. When we think of original reactions, we talked about reactions in the past. We said that the reactions would go to completion, that we would produce all the products. But that's not always the case. Sometimes what happens is our products can go backwards and react and form our products again. And that's what's going on at that equilibrium point. The nitrogen and hydrogen react in what's called the forward reaction, and then the ammonia breaks down in what's called the reverse reaction. And when we talk about chemical equilibrium, when we look at this, I'll come back to that in just a second. The rates of the two will become equal to each other. Let's come back to that in just a second, actually. Okay, so the forward reaction works, and then the reverse reaction. What happens is the rates of those two reactions, the forward reaction, is equal to the rate of the reverse reaction. Now notice, the amount of hydrogen, the amount of nitrogen, and the amount of ammonia are not equal to each other. A lot of students think that equilibrium is referring to the amounts of material, the concentrations of them. But in reality, what equilibrium is referring to is not the concentrations, but to the rates. The rate of the forward equaling the rate of the reverse. So just like with those water molecules, I produce the ammonia, and then it breaks right back down into the nitrogen and hydrogen. Creates this, breaks back down. So it's almost as if they're to us, the reaction will look like it's no longer working. So the reaction starts producing products, and then the products break back down. It looks like everything is staying the same. Okay. Now we could do this again, and this time starting with ammonia, okay, and letting the ammonia break down into nitrogen and hydrogen. Okay. Again, you'd have the balanced equation. And notice the double arrows that I'm using. I tend to use the half arrows. You can use full arrows if you want. It's up to you. But I'm just showing the forward reaction and the reverse reaction. So this is called an equilibrium equation. It's different than reactions where we just have a single arrow, because this is telling us that this reaction gets to what's known equilibrium. This is only going to occur if I put this into a sealed container, by the way, just like with the gym bag and the wet towel. All right, so if I let this happen again, I start with the ammonia this time. Again, ammonia is going to get used up. It's going to go down while my nitrogen and hydrogen start to get accumulated. Ammonia goes down, nitrogen and hydrogen start to increase. And eventually I get back to this equilibrium position where they no longer change. So to us, it looks like the reaction is stopped. But in reality, it's constantly producing this and producing this backwards. Okay? I know equilibrium is a little confusing in the beginning to kind of understand, so just do your best to get it, and we'll talk about it more in class. But let's say we have a hypothetical reaction of A converting to B. Okay, start with A. Remember the brackets, in case you forgot, brackets mean concentration, so that means molarity. Okay, so we're starting with the concentration of A being 0. Eventually the A is going to start to get used up. No, sorry, the A isn't 0, the B is 0. The A is going to start getting used up, and then the B is going to start to form. That's what happens initially. Well, eventually I get enough B in the reaction that the B starts to react backwards and starts to produce the products again. Or sorry, produces the reactants again, which is A. Okay, as that happens, eventually we get to a point where it looks like the reaction stops. Okay, but the reaction, like I said, is always happening. Now, at that point, if we look at the rates, this is a fancy little equation for the rate. Don't worry too much about this. I'm not going to ask you about that. But the rate is the speed, how fast the reaction is working. Now, you should know that if I have a lot of A, right, if the concentration of A is high, we would expect the speed of that reaction to be quick, right? It would quickly form B. And as A gets used up and I have less and less of it in the reaction, it's going to start to slow down and it's not going to produce B as much. Well, if I'm producing B and I'm increasing the concentration, wouldn't it make sense that the speed of B would start out slow, and then it would start to speed up and go faster and faster and faster, and eventually the rate of A slows down, the rate of B speeds up, and those two rates become equal. And as I said before, the rates are equal, not the concentrations. But take a look at this though, because if we look at how much A that I have at equilibrium, when I get to this equilibrium position, notice that I have more A than I do B. Since I have more A than I do B, I say that I favor the reactants, and I'll talk about that a little bit. So I say I favor the reactants. The reactants are favored in this reaction. I have more reactants than I do products. Alright, so some things about equilibrium. First of all, equilibrium occurs when the opposing reactions have the equal rates. Okay, at equilibrium, the concentrations of the products remain constant, not equal. They just remain constant, so it looks like the reaction is no longer working. the rate of the products formed is equal to the rate of the formation of the reactant. So that's what I was saying before. The rate of the products, the forward reaction, is equal to the rate of the reactants, which is the reverse reaction. Okay?